let's see here, 1 implies 3. Oh, excuse me, 2 implies 3. We argued that previously. 3 implies 1. I think 3 implies 1 is kind of diffeomorphic to a torus, implies the existence of a non-vanishing vector field. That's perhaps a little bit surprising. Here's the proof of that. For 3 implies 1, for a torus with the usual parameterization, you can either use the partial velocities, xu or xv, for a global non-zero tangent field. So it's kind of cool, right? For the torus, the xu and the xv, when they come back, when they circle back to where you kind of have that like jump, if you wanted to, like, you know, if you wanted to just cover the torus once with the patch, the torus patch, it's not a bad problem when you get back to where you started, because the xu at the end is pointing in the same direction as the xu at the beginning. In contrast, it doesn't work out quite that way for the sphere. Or does it? Something's wrong with the sphere. I think it's the north pole in terms of the partial velocities, but anyway. I guess theta hat's okay on the sphere. It's the phi hat that gives you trouble in my usual theta phi language. But now here is Gauss-Bonnet for a polygonal region. All right. But what's most interesting is Gauss-Bonnet for a triangle. So here it is. Finally, we got back to it. The angle excess theorem. And this is I think this is a fitting place for our course to end. So Gauss-Bonnet for a triangle in a geometric surface says that the integral of the curvature over the triangle is equal to the integral of the geodesic curvature on the edge of the triangle, right? Plus that is equal to 2 pi minus the exterior angles at the vertices of the triangle on the surface. But in terms of interior angles, that's the sum of the interior angles minus pi. Now this, what's that?
0.
Doesn't have to be 0.
What, the triangles add up to 180?
But triangles don't always add up to 180 when they're on curved surfaces.
Yeah.
And also, triangles don't always add up to be 180 when they're not made with geodesics. See, a geodesic has geodesic curvature 0. So if we made the triangle to have sides which are made from geodesics on the surface, then this term drops out. And then we're just left with the result that the integral, the total curvature of the triangle, is equal to the sum of the interior angles minus pi. If the curvature of your surface is 0, yes, for a geodesic triangle, a triangle made with straight edges, yes, the sum of the interior angles has to be equal to pi. But if the curvature is non-zero,
Yeah, like on a sphere.
like on a sphere or like in the hyperbolic plane,
Yeah.
you can have an excess or a defect, either too much or too little. But here it is. So if the sides are geodesic and the curvature is constant, if the curvature is constant, the integral of curvature is just curvature times area. So we have curvature times the area of the triangle is the sum of the interior angles minus pi. This is the lauded angle excess theorem. So if the curvature is positive, what does that mean? That means that the sum of the interior angles is greater than pi. If the curvature is negative, it means that the sum of the interior angles is less than pi.
You get a negative triangle?
Yeah, sure. In a like a hyperbolic space, negative curvature. In a elliptical space, like here.
Yeah.
So here's the picture. So for this kind of, the sum of the interior angle is larger than pi. And this kind of triangle inside the Poincare disk, you have angles less than pi. And you'd say, well, and the reason that me saying that makes sense is because it turns out that these are conformally related to our usual notion of Euclidean geometry in the sense that the the local angles that we're visualizing between tangent line segments are in fact the real, quote-unquote, real spherical geometry angles or hyperbolic geometry angles. They match the underlying Euclidean geometry. So anyway, yes, the triangle can have more than 180 degrees on a positive curvature space, and it can have less than 180 degrees on a negative curvature space. And in the context of Euclidean geometry, where curvature is 0, the sum of the interior angles has nothing to do with the area of the triangle at all. It's just 180 degrees, no matter how big or small your triangle is, which of course we know. But, so there it is. I think I showed you guys this triangle before, right? Like the eighth of the sphere, yeah. It's got 3 90-degree angles, you know? And we can make good on the particulars of this example because it's got pi plus pi over 2. Pi is 1/8 of 4 pi. The area of the whole unit sphere is 4 pi. So 1/8 of 4 pi is the pi over 2. I guess that's the pi over 2, yeah. Sorry, this term, I got my terms mixed up, but. Anyway. So, any questions? Now, this connection, finding this, so there's something very precious about this result we've seen, this Gauss-Bonnet theorem. What it's doing is it's saying there's something we can calculate from differential geometry, right, which is linked to something in topology. There are a few other results like this known, but they're precious and rare, and we're always looking for more of these results. But yeah, trying to connect 2 fields of math, and there is a more complicated version of Gauss-Bonnet, but that's, I'm trying to remember where that's talked about, but I mean, this is a problem that persists, is like trying to understand what's the interplay between topology and differential geometry. This is an ongoing question, which is by no means settled. There are open and difficult questions. And so anyway, it's a fun part of math to work in. I'll stop there for this semester.